Hello everybody, welcome to Silence Abounds Science at Home, where we will discover home lab magic. We will look at scientific principles, concepts, reactions by performing experiments in the comfort of our home. We will cover chemistry, biology, microbiology, microscopy, even forensic science. Welcome to my channel. Hello, in today's video, we're going to be looking at the stoichiometry of a single displacement reaction. Wow, that's a bit of a mouthful. Let's break it down. Stoichiometry, what does that mean? In a chemical reaction, matter can neither be created nor destroyed according to the law of conservation of mass. So the products that come out of a reaction must equal the reactants that go into the reaction. This means that the amount of each atom that you put in must come back out. Stoichiometry is the measure of the elements within a reaction. So it's all about balancing a reaction. Like I said, the reactants must equal the products. In a single displacement reaction, this is a reaction where one element trades places with another element in a compound. In these kinds of reactions, one element displaces another from a compound to form a new compound and the displaced element. Generally, the more reactive an element displaces a less reactive element in a compound based on this reaction. In this video, we're going to study the mole relationship in a single displacement reaction where zinc replaces copper to form copper and zinc sulfate. Zinc metal is above copper in the activity series, and therefore zinc will replace copper in solution. The zinc metal is oxidized as it loses electrons, and the copper ions are reduced to copper metal as they acquire electrons. Based on the stoichiometry for the reaction between zinc and copper sulfate, each gram of zinc will need 15.3 mL of a 1 molar copper sulfate solution to completely react. Since copper sulfate needs to be in excess, we're going to use a 10% excess of that 15.3 mL 1 molar copper sulfate solution. So, using the equation shown, the ratio, if you look at the reaction, or the calculation I should say, so we can use 10% excess. So that means 16.8 mL of copper sulfate will react with 1 gram of zinc. So what we're going to do is we're going to use 10 mL of copper sulfate in our reaction, and we're going to weigh out about 0.6 grams of zinc to get that equation right. Okay, so just that was a little bit complicated. So the ratio of the excess, that 10% excess, is equal to 16.8 mL of copper sulfate to 1 gram of zinc. But what I'm going to do is I'm going to just use a smaller quantity. I'm going to calculate, and it works out to be 10 mils of copper sulfate with 0.6 grams of zinc. So let's start the experiment. What you need for this experiment is copper sulfate, your 1 mole copper sulfate, and I've already made a solution of copper sulfate. You need acetone, and then you need some zinc powder. I put a link in the description of the video of all the resources that you will need in order to set up your home lab, and what you need and where you can buy the chemicals and equipment to do this experiment in your home too. All right. So I've got the copper sulfate, and now next I need to weigh my zinc. So the first thing I'm going to do is weigh some zinc powder in a 150 ml beaker. And I have my balance here. And I want about 0.6 grams of zinc powder. Which is not a lot. Okay, so I got 0.6 grams of zinc. And then I'll put that aside. And then what I want to do next is I want to heat some of my copper sulfate. So I'm going to use 10 mLs of copper sulfate. So I'm going to get a pipette, and then I'm going to measure out 10 mLs of copper sulfate. Like so. Okay. And now what I want to do is I'm going to put all this into a 50 ml beaker. And I want to heat this, so I'm going to heat it on my hot plate. And I don't want it to to boil. So I'm just going to heat it until bubbles start to form, but not go to boiling. Okay, so I just wait for that to heat. Okay, it's starting to bubble. So I'm going to remove the beaker from the burner. I'll turn that off for safety. And then what I'm going to do is I'm going to add the hot copper sulfate to the zinc powder. Okay. And I'm going to mix it, stir it slowly with a glass stirring rod. just going to give that a good stir. And if you notice, the liquid has turned clear. Okay, it's turned clear. Okay, so I'm just going to leave that in there. And while we're waiting for the reaction to take place, I'm going to get another beaker and I'm going to make a water bath. Okay, I'm going to add about 75 mils of just water and I'm going to heat that up. So I'll put my hot plate back on and I want to heat that up because I'm going to put this beaker into the water bath. So what I want to do now is the reaction's finished. There's no blue left in solution, so it's been replaced by zinc, and what I've got now is copper. I know it still looks black, but we now have copper, and we need to wash that out. So what I'm going to do is I'm going to add 10 mLs of water. Doesn't have to be accurate. Okay. And I'm going to wash the copper. Like so. Just give it a mix. And then I'm going to let that settle. And then what I'm going to do is I'm going to decant and remove the liquid. And I'm going to do that a couple of times to wash the copper. And then we will then dry it by placing it in a hot water bath, washing it with acetone, and the acetone will help dry off the copper that is at the bottom of the beaker. So I'm just waiting to remove some of that liquid. And I got another beaker here that I'm going to siphon off the liquid. And you don't want to take any of the copper if you can help it. Because what we're going to do is we're going to calculate how much yield we made, how much copper we made from this experiment, from this reaction. So this is not easy to do. So if I move it like this. Okay, fortunately I get most of the liquid off. And I didn't disturb the copper at the bottom. Okay, so now I need to do that again. Add another 10 mLs of water. I'm going to actually add a little bit more just because it's easier and there's a little bit more liquid. So I'm going to give that a mix. Okay, and we again let the copper settle to the bottom of the beaker. I'm going to heat up the water again, so my water bath is ready. Okay, so again, I'm going to gently tilt the beaker and remove the water as before. Doing it as gently as I can, not to suck up any copper. So because of the blue color disappeared, we know that this reaction took place and the zinc was replaced by the copper. And what we have at the bottom of the beaker now is copper, even though it doesn't have the copper color, but okay. So now what I want to do is add 10 mL of acetone. So this is the drying phase. We want to dry the copper sulfate. So I'm going to measure 10 mL of acetone. Switch it around. We're going to let it decant again. It shouldn't take long. And we're going to remove that acetone layer. And then we're going to add another 10 mL of acetone. All right. Then I'm going to add the final 10 mL of acetone. Like so. Mix it up again. Let it settle. Okay, so it's okay if you leave a little bit of acetone behind because we're now going to put it into the water bath to evaporate off. Okay, so I'm going to put this beaker into this water bath. And now I'm just going to leave that to evaporate out to dryness. So the acetone now has had plenty of time to evaporate off from the copper. So I'm just going to dry the beaker. And what you see, what is produced, is a dark reddish brown precipitate. And that is the copper. Okay, so now what I want to do is I want to weigh it because I want to calculate my yield and I want to calculate how much copper is has been produced. So I have my log and I'm going to record the weight of the beaker and copper. So now we want to do some calculations to calculate the percent yield of copper and to see whether the moles of copper to moles of zinc is on a 1-to-1 ratio, which the reaction formula suggests. So I have the mass of the beaker, which was 108.8 grams. The mass of zinc used, remember I weighed 0.6 grams. The mole amount of zinc used is the mass, 0.6, divided by 65.38, which equals 0.009 moles. The volume of 1 molar copper sulfate was, we used 10 mLs. The mass of beaker and precipitated copper, so after the experiment and when the precipitate dried, I weighed it again and it was 109.5 grams. So the mass of the copper precipitate is 0.7 grams. So it's 109.5 minus 108.8. And then I want to calculate the amount of copper produced. So I got the mass of 0.7. So it's 0.7. Divide that by the mass, atomic mass, which is 63.55. And that equals 0.01 moles. Okay, so in theory, the mole amount of copper produced should equal to the molar amount of zinc used. So we should have got 0.009 moles of copper to equal the amount of zinc used. So the theoretical mole amount, which is what I just said, should be 0.009. Okay, so how do we calculate the percent yield? So the formula for calculating percent yield is the experimental yield divided by the theoretical yield times 100. So our experimental yield is 0.01, and then the theoretical yield is 0.09 times 100. That equals 111%. So the ratio is calculated as 1.2. So we're just above the yield of 100%, so we're just a little bit over, and our mole ratio is not quite 1-to-1. And we'll discuss maybe some factors that might contribute why we got more of a yield and that we're just slightly out with the ratio. So I'm happy with our results that we got from our experiment. A single displacement reaction showed that copper and zinc displaces copper, and we were left with the copper precipitate, the brown, reddy brown precipitate. So our yield was 111%. So it was a little bit more than 100%. You expect to get a yield, or what you're looking for is a yield of about 100%. So there are factors. So if you were to do this experiment as well in your home, you may get a yield that's less than 100%, or like me, you may get a yield above 100%. Well, so what are the contributing factors that may cause a variance? You know, science is not always 100% perfect, and there are a lot of factors that can produce different yields. So you can actually repeat this experiment 2 or 3 times and get different yields. And what is a good idea is to do this a couple of times, changing the way you're doing things a little bit, especially with the drying, and see whether you can get that 100% recovery. So if your yield is under 100%, less than 100%, a couple of factors that might cause this is the loss of copper during the washing. The decanting is very delicate, and it's very easy to actually siphon off or pipette some of the copper that's remaining. So that could give you a less than 100% yield. Also, there are soluble impurities in the zinc that may cause a yield of less than 100%. Whereas improper washing and drying of the copper could increase the yield. So maybe I was a little bit rushed during the process, or I didn't dry the copper enough. That gave me a yield of 111%. That's quite easily done. I wasn't that far away from 100%, so that's why I'm happy with my results. Also, incomplete reaction can leave some of the zinc in the copper sample. Again, that may contribute to the color as well, not being brighter. I may not have reacted the zinc completely. And then there are also insoluble impurities in the zinc that may increase the percent yield. So to summarize, there are rules for the prediction of a single displacement reaction, and the simple way to determine whether a single displacement reaction is going to occur is to look where the elements appear in the periodic table. The periodic table can help predict whether single replacement reactions occur. The relative reactivities of the two elements can determine whether one element will replace another element from a compound. For example, if you look at the halogens, this is the order of reactivity. So you can see that fluoride will replace chloride, chloride will replace bromide. But iodide will not replace bromine. Iodide will not replace chloride. Okay, because that is the least reactive halogen in the series. Another example is metals. Here is the series of reactivity from the most reactive to the least. As you can see, copper will replace silver, will replace mercury, and so on. And cation replacement. Cation is a positive charged ion metal. One cation replaces another, and here is an example. Then you have anion replacement. Anion is a negatively charged ion metal, and here is an example of an anion replacement. You can get all my recipes for all my experiments that I perform on my Patreon page. Also, if you follow me on my Patreon page, for members only, you can get exclusive videos that are more extended and more extensive than I'm posting on YouTube. Those videos are for paid members only and can be found on my Patreon page. Please remember to subscribe to my channel. It doesn't cost you anything, and it helps support my channel and produce more and more videos. Please hit the like button and the share button also. In my description, I list all my resources of where I get all my lab equipment, chemicals, my kits, everything I use for my videos can be found in those resources. I also recommend 2 books, which are my Bibles for home science experiments. Here is the illustrated guide to home biology experiments. They're published by Maker and can be found at makershed.com. Also, check out the homescientist.com website, where you can actually buy all the kits in order to do all the experiments in these books. These are my Bibles, and a lot of the work, a lot of my videos are inspired by these books. Here is another book, which is the Illustrated Guide to Home Chemistry Experiments. And again, this is where I get some of my ideas for these experiments from, and I highly recommend them. Please contact me in my email address. I would love to hear your comments, your thoughts on my videos. Also, please send me photos and videos of you doing home experiments as well. I like to see you doing your own experiments at home. Until next time, keep on experimenting.